It's a pleasure to chair this first plenary session of the Formal Philosophy meeting, and it's also a pleasure to enjoy this meeting organized by the International Laboratory for Logic, Linguistics and Formal Philosophy, chaired by Professor Elena. And we'll have the first talk by Professor Gila Sher from the University of California, San Diego.
Yeah.
She's going to speak about invariance as a basis for necessity and loss. We will have 45 minutes.
Okay, it's a pleasure to be here, and I would like to thank Elena very much for inviting me and the organizers for organizing this. And I will try to be quick so that we have some time for questions. Okay, so the talk is Invariance as a basis for necessity and laws. Many philosophers find necessity baffling. Humeans in particular are deeply disturbed by the thought of necessary laws of nature. They view the idea of such laws as an arcane idea of secret, inexplicable, mysterious powers governing the world. In this talk, I offer a down-to-earth yet systematic explanation of necessity and laws in terms of invariance. The idea of invariance. Invariance is generally an important and highly explanatory notion, widely used in all branches of knowledge, from logic to physics. We have Wigner in physics, more contemporary James Woodward. We have Nozick in philosophy. We have Klein, the Erlanger program in geometry, Tarski in logic, and so on. In this talk, I regard invariance as a relation. X is invariant under Y. I focus on a type of invariance that is applicable to all fields of knowledge. Roughly, the idea is that generally X and Y can change, so different things can be invariant under different things. What I will have is property X is invariant under replacements of individuals Y. The underlying idea is this: properties in general are selective. They pay attention or are attuned to some features of objects but not to others. Accordingly, they distinguish between some objects and not others. For example, the property has a mass distinguishes between stones and numbers. It applies to stones, but it does not apply to numbers. But it does not distinguish between stones and stars. It applies to both. The same holds for the property is subject to gravity or partakes in gravity. This can be expressed in terms of invariance. The property partakes in gravity is invariant under all one-to-one and onto replacements of stones by stars. But it is not invariant under any one-to-one and onto replacements of stones by numbers. Another way to put this is, if you replace stones by stars, you replace some objects that partake in gravity by other objects that partake in gravity. So the property partakes in gravity is not affected. It is invariant under these replacements. But if you replace stones by numbers, you replace objects that partake in gravity by objects that don't, and the property partakes in gravity is not invariant under such replacements. Now, the selectivity of properties introduces structure, invariant structure into the world. Some properties are more selective than others, have a higher degree of invariance, and different properties are invariant in different ways, are invariant under different replacements of individuals. But to understand the selectivity of properties, we have to take into account not just actual but also counterfactual individuals. Let me give you two examples. First, coextensional properties. The properties has a heart and has a kidney. These properties are invariant under the same replacements of actual individuals because they have the same actual extension, but not under the same replacements of counterfactual individuals. So if we want to understand the difference between them, we have to take into account counterfactual individuals. But even when we go to regular properties, like partakes in gravity, we don't understand the pattern of selectivity or invariance of partakes in gravity if we don't realize that if had another moon, it would partake in gravity just as much as its actual moon. Partakes in gravity would not distinguish between them. So again, to understand the broad scope of partakes in gravity, we have to take into account counterfactual physical individuals. This notion of counterfactual individual is not a philosophical term of art as I present it, and it is not associated with any specific philosophical theory of counterfactuals. It is the everyday pre-theoretic notion that we use in mundane discourse as well as in all the sciences. For example, suppose we want to design a medicine M. Then we have to ask very many counterfactual questions about it. Would medicine M have been effective had this or that counterfactual situation been the case? This is a common notion and there is nothing mysterious about it. Now, my claims in this talk are the following. 1. Every property is invariant under some one-to-one and onto replacements of individuals. 2. Some properties have a higher degree of invariance than others. 3. The higher the degree of invariance of a given property, the greater the degree of generality and necessity of its laws or principles. That means that if the degree of invariance of property P1 is greater than that of P2, then the degree of necessity of the principles governing P1 is greater than the degree of necessity of the principles govern P2. So this is the crucial thing, connection between invariance and necessity. And this extends to fields of knowledge. The higher the degree of invariance of a given field of knowledge, the greater the degree of generality and necessity available to its laws and principles. The significance of these points, of these claims, are that given that every property is invariant under some one-to-one and onto replacements of individuals are, some properties, including some properties recognized by Humeans, have a fairly high degree of invariance, and there is a connection between high degree of invariance and high degree of necessity and laws, and none of 1 to 3 are mysterious, it is neither surprising nor mysterious that there are necessary laws of nature, namely laws governing, describing the behavior of highly invariant natural properties. Okay, now let me go over each claim and explain why and how it holds. Claim 1. Every property is invariant under some one-to-one and onto replacement of individuals Y. R, sorry. My notation is a familiar one. D is domain, a non-empty set of individuals. R is a replacement function, any one-to-one function on some D. The claim is for every P, there is an R such that P is invariant under R. Now this is trivial since every property is invariant under the identity replacement. Functions are that replace each individual in D by itself. But my claim is stronger. Properties in general are invariant under more than just the identity R's, and the examples I gave before show it. Claim 2. Some properties have a higher degree of invariance than others. Some properties, P1, P2, are such that the degree of invariance of P1 is greater than that of P2. Example, the degree of invariance of is identical to is greater than that of partakes in gravity. Intuitively, partakes in gravity is invariant under replacements of physical individuals by physical individuals, but not under replacements of physical individuals by numbers. But identity is invariant under both. So it is invariant under more replacements. It has a higher degree of invariance. Claim 3. The higher the degree of invariance of a given property, the greater the degrees of generality and necessity of its laws and principles. That is, if the degree of invariance of P1 is greater than that of P2, then the degree of necessity of the principles of P1 is greater than that of the principles of P2. Now, we saw that the degree of invariance of is identical to is greater than that of partakes in gravity. In fact, is identical to is invariant under all R's, not just under more R's than physical properties, but in fact under all R's whatsoever. It has a maximal degree of invariance. To see that, take any R and any pair of individuals AB. The image of AB under R is some pair of individuals CD. Because R is one-to-one, A is identical to B if and only if C is identical to D. That is, identity is invariant under R, and this holds for any domain whatsoever and any R. Now take any principle governing identity. For example, the identity principle, every individual is identical to itself. Claim, since the property is identical to does not distinguish between any individuals, the identity principle which governs it cannot distinguish between any individuals either if it describes it correctly. This is the key point. If a property P does not distinguish between certain individuals, its principles cannot distinguish between them either. Where by the principles of a property P, I understand here the principles that describe the behavior of P over all objects, actual and counterfactual, to which it applies. This means that the more individuals a property does not distinguish between, the greater the scope of its principles, the actual counterfactual scope of its principles. i.e. the more one-to-one and onto replacements of individuals a property P is invariant under, the greater the actual counterfactual scope of its principles. Back to identity and its principle of identity, every individual is identical to itself. Let us say that a principle is general if it has a large actual scope. And let us say that it is necessary if it has both a large actual scope and a large counterfactual scope. Since the principles of identity apply to all individuals whatsoever, they are to all actual individuals, they are maximally general. Since they apply to all counterfactual individuals as well, they are maximally necessary. In contrast, partakes in gravity is not maximally invariant. The principles of gravity are not maximally general or maximally necessary, i.e. the degree of necessity of the principles or laws of identity is greater than that of the principles or laws of gravity. And similarly for all other properties and their laws and principles. Claim 4. The higher the degree of invariance of a given field of knowledge or discipline, the greater the degrees of its generality and necessity. i.e., if the degree of invariance of field 1 is greater than that of field 2, then the degree of necessity of field 1 is also greater than that of field 2. Explanation. Let us associate with each field of knowledge a characteristic property. For logic, it'll be is an individual simpliciter. For physics, it'll be is a physical individual. For biology, is a biological individual. And let the degree of invariance of a field F be the degree of invariance of the characteristic property P of F. And the degree of necessity of F, the degree of necessity of the principles or laws of P. Then claims 4 follows from claim 3. It is easy to see that the degree of invariance of logic is greater than that of physics, hence the degree of necessity of logic is also greater than that of physics. However, the degree of invariance of physics is still fairly high. Physics is invariant under all replacements of physical individuals by physical individuals. Hence, the degree of necessity of physics is also fairly high. Thus, take again partakes in gravity. It is invariant under the same hours as is a physical individuals. That is, degree of invariance of partakes in gravity is identical to that of is a physical individual. Therefore, the degree of necessity of principles of gravity is very high, is fairly high. This means that the principles of gravity, the principles that describe or govern the behavior of gravity over all individuals, actual and counterfactual, to which it applies, have a sufficiently high degree of necessity to count as laws. And there is nothing surprising or mysterious about that. Now, so far I talked without giving any formal definitions. Let me briefly give a few formal definitions. Let R be from D1 to D2 be a one-to-one and onto function, a bijection. Let P1 and P2 be properties. First, definition of P is invariant under R. First, if P is a one-place first-level property, invariant P under R, if and only if, for every x in the domain D1, X has the property P if and only if R of X has the property P. When P is a one-place second-level property, the definition is invariant P under R if and only if for every D1 where D1 is a first-level property restricted to the domain D1, PD1 is a first-level property restricted to D1, PD1 has the property P, the second-level property P, if and only if its image under R, image of PD1 under R has the property P. And R star is the image of PD1 under R. Definition of maximal invariance. P is maximally invariant if and only if for every R, P is invariant under R. And finally, definition of the degree of invariance of P1 is greater than that of P2. Case 1, at least one of P1, P2 is maximally invariant. Then the degree of invariance of P1 is greater than that of P2 if and only if the class of all R's such that P1 is invariant under R properly includes the class of all R such that P2 is invariant under R. So greater than or higher is in terms of inclusion, proper inclusion. Case 2, neither P1 nor P2 is maximal invariant. Same, but R is restricted to domains with individuals that had at least one of the properties P1, P2. If P1, P2 are first-level properties. And PD1, PD2, such that PD1 holds of P has the property P1 and P prime D2 has the property P2 if P1 and P2 are second-level properties. Okay, now I would like to talk about the philosophical results for logic, mathematics, and science. First, all logical properties are maximally invariant. Therefore, all logical laws, also all logical consequences and truth have a very high degree of invariance. In fact, extremely high, maybe maximal degree of invariance. Maximal invariance captures the idea of formality in the objectual sense. High structurality, I talked about this in my earlier talks here. I will not be able to go into detail. 3, all higher level mathematical properties are formal. That is, therefore, all higher order mathematical laws have a very high degree of invariance. So, maximal degree of invariance means formality, means high necessity, and since higher level mathematical properties are formal, their laws are highly necessary. Given that all first order mathematical individuals and properties are correlated with formal properties, the number 1 with the second level cardinality property 1, 2 with 2 is even, with the third level property is even. First order mathematics can be viewed as representing formal higher level mathematics. And that means that first order mathematics derives its strong necessity from that of formal higher level mathematics. Results for metaphysics and science. For metaphysics, a necessity comes in degree. There's not just necessary or not necessary, but there are degree of necessities. And similarly, therefore, possibility comes in degrees. There are larger and smaller spaces of possibility. For example, the space or the logical space of possibility is greater than the physical space of possibility, which is greater than the biological space of possibility. This enables us to explain various things. For example, the difference between accidental and necessary generality in physics. Two well-known examples. There are no very large, say 1 mile in diameter, spheres of gold on Earth, and also there are no very large spheres of uranium on Earth. Fact. A is due to the fact that there is not much gold on Earth, which is an accidental fact. And B is due to the fact that the structure of uranium rules out large uranium spheres, which is something which is essential, not accidental to uranium. Now, within the space of logical possibility, from the point of view of logic, both are accidental. Because logic, from the point of view of logic, it will not distinguish between uranium which is structured, actual uranium which is structured in this way, or counterfactual uranium which is structured differently. But within the space of physical possibilities, A is accidental and B is necessary. So this idea of invariance and its relation to necessity and degrees of necessity, spaces of possibilities, can explain this fact. A is physically accidental, B is physically necessary. Result for mathematics and science. The view that mathematical properties are maximally invariant or formal leads to a new answer to Wigner's question, famous question, how is mathematics applicable to physics? Our answer is formal properties, being maximally invariant, don't distinguish between individuals of any kind. They apply to all individuals, including physical individuals. That is, mathematical laws apply to physical individuals. And there is nothing surprising or special about that. It's really quite obvious. Result for philosophy and science. We have already seen how invariance theory dissolves Humeans' worries about necessary laws. If there is invariance in nature, there is a groundwork or infrastructure for necessary laws in nature. Another worry concerning laws of nature centers on their abstractness. Humeans say that to abstract is to abstract from what is real. To falsify, to abstract is to falsify, to ignore what is real. Abstraction, they say, resides in us, not in nature. Nature includes only particular objects and their particular properties. Invariance theory says no, this is not the case. According to invariance theory, the real properties of real objects are selective in character. Any property of real objects is selective in character. They themselves ignore that is abstract from various features of differences between objects. That is, real properties are already abstract in nature. Some of these properties are abstract to a considerable degree. These are the highly invariant physical properties such as gravity. Since invariance, hence abstraction, is built into nature, necessary laws are built into it as well. The last point is philosophical result concerns realism. Silos in 2014 says the reality of laws is based on the reality of patterns and regularities. Invariance theory supports this and strengthens it. Maximal invariance is a mark of formal patterns. Physical invariance is a mark of physical or physical and mathematical patterns. If and to the extent that there are objects and properties in nature, there is a network of invariances in nature, and these are the basis or one of the bases for the reality of natural patterns, regularities, and laws. Okay, let me conclude with the limits of invariance theory, what it does and what it doesn't do. It is important to be clear about what invariance theory purports to do and what it does not purport to do. What it purports to do is this: provide a down-to-earth, non-mysterious, yet systematic basis for the possibility of necessary laws in various fields, physics, mathematics, logic, etc. In the case of maximally invariant fields, such as logic and mathematics, it actually establishes the presence of necessary laws in these fields. In the case of non-maximal invariant fields, such as physics and biology, it establishes a groundwork or an infrastructure for necessary laws of various degrees of necessity. It shows that there is a theoretical basis, a non-mysterious theoretical basis for the existence of such laws. What invariance theory does not purport to do is it does not purport to rule out additional philosophical guidelines for and even requirements on laws and law-supporting properties. For example, it can accept a Goodman's requirement that law-supporting properties will be projectable, or David Lewis requirements that laws of nature should have a balance between naturalness and strength. 2. Invariance theory does not purport to determine what the laws of nature are, or even if there are laws of nature. This is left for scientists to do, partly on pragmatic grounds, but mostly and primarily by probing the world. 3. The invariant infrastructure of laws of nature is limited to laws that describe the behavior of highly invariant properties over all objects to which they in principle apply. It does not apply to laws of other kinds. For example, it doesn't apply to stipulative laws, which have nothing to do with the nature of the properties they hold of. They are just stipulative. And it does not apply, at least not directly, to singular laws. For example, laws concerning the speed of light, unless this is needed for highly invariant laws. And again, this is something that is left for the physicist, not for the philosopher of invariance to determine. Such laws require either a non-invariant explanation or an extension of the present invariant explanation, but it does apply to laws, to many of the most important laws of nature, such as laws of gravity, laws of mass, laws of motion, and so on. Thank you.